All right. It is matrixology is full of magic, right? So, and this is just probably just another moment for you, but it's a pretty great one. All right. So, symmetry and a spectral theorem. We've seen this great thing, diagonalization. The game now is to understand what happens when we start with a symmetric matrix. And we're going to focus on real symmetric matrices. This can be generalized to things with complex numbers, but that's our game is going to be about real symmetric matrices, right? So we know some beautiful things. I know that I can erase things. So diagonalization is fantastic, right? Really good. Enables us to do all sorts of things. Very nice. This is important. So A can only be diagonalized if it has n linearly independent eigenvalues. Very important. So let's get that right. So this is an n, we're talking about an n by n, of course, right? So n, yeah. Okay. So we know if the eigenvalues are distinct, we're okay. If eigenvalues are repeated, we can have trouble. So this is potentially, I should be clear about that. It's not always true, right? The identity has repeated eigenvalues. They're all ones, and the eigenvectors are fine. So we may not end up with a full eigenspace is the story, right? So we might not have, n linearly independent eigenvectors. And for any repeated eigenvalue, that's where the trouble happens, right? So if you have an eigenvalue that's repeated 3 times, so your eigenvalue 7 appears as a lambda minus 7, right? To the power of 3 in the characteristic equation. So it's repeated 3 times. Then when we solve to find the eigenvectors associated with, we want to find a 3-dimensional eigenspace. We may not find that. So, okay, that's our concern. We'll deal with that in a second with symmetric matrices. There are a couple of extra new pieces here. Okay, so we knew this. So if one or more eigenvalues is 0, then this is true. Right? There's no inverse. Right? That's connected to a pivot missing, that the rows and columns of A are linearly dependent, that the null space is not just 0, lots of pieces. But A may still be diagonalizable, right? So these are somewhat separate things. It's to do with the eigenvectors in this case. It's fine to have an eigenvalue of 0. That can have a happy eigenvector, right? So these are different things. So that's a useful thing to understand. All right, just to add to your knowledge. Right, so here's the big deal for this little piece. So it's real, so A is real and symmetric. Let me just make that clear. That means A is A transpose and Aij is real. Right, for all Ij. Right? All the entries are real. Then there's just a sort of a little lead into it here. We'll always have n linearly independent eigenvectors. It's always diagonalizable. But there's actually sort of more here, right? So there are two bigger things. So it's always, okay, so always diagonalizable. Good. Big deal. And then huge is this. That's a pretty big deal. All of A's eigenvalues are real. So that means we only have, right, lambda can be negative or positive, but a real number, so it can be something that stretches or shrinks depending on the magnitude, and it could flip. But that's it, right? So we haven't really done this, but complex, talk about a little bit today, but complex numbers for eigenvalues encode rotation. So we know it's not a rotating thing. And then, so it's just sort of a stretching and maybe a flipping thing. And then this piece. This is rather remarkable. A's eigenvectors form an orthogonal basis for Rn. Of course, you can make it an orthonormal one. So it's not just that there's a full set of them, they're actually at right angles to each other. That's pretty surprising, I think. It should be pretty surprising. So that's kind of amazing. So we'll prove that in one case fully, and then sort of just to demonstrate how how that might hold up. That's in the next piece. So this is just going to be kind of the story with an example, and then the next piece will kind of argue for why these things are true. So we're very excited about this. You can tell. Just calm down. So we're very excited. So we get so excited that, you know, you just start sending tweets out. I know it's Snapchat or whatever, Instagram. That we replace, so instead of just having the eigenvectors in columns, we put the unit eigenvectors. So let's make that clear. So these are unit vectors. And this is a special kind of matrix that we've looked at before, which is a orthogonal matrix, even though it's got really sort of orthonormal. So it's got this stack of vectors lined up that are all at right angles to each other. And we have so we have an orthogonal matrix. Right, we're going to use Q. We're going to go to Q. Right. And we know the inverse of Q is fantastic, right? It's really great. It's just the transpose of Q. Really wonderful thing. Wonderful thing. So this saves a lot of trouble. Right, we can do a lot of things here. And so now we have, this is a new level of majesty. I have to do this. A is not just, so there's still a lambda in the middle, but instead of S, we have a Q, and instead of S to the minus 1, we have Q transpose. So that is terrific. Just excuse me while I make a bit of a mess here. So, yeah, that is huge. Wow. Right? Wow. Okay, good. There it is. So this is a wow. Let's go a little step further. Okay, so now we have this Q lambda Q transpose. Because it's a transpose, we get some nice things. There's a wonderful thing we do. So here it is. We're just taking the transpose, just laying these unit vectors in rows. Here they were as columns. If we multiply this through, well, first of all, the lambda ones multiplying through, they just pick up each row, right? Lambda 1 times v1, lambda 2 times v2, lambda n times vn, and then they're stacked like this. And then we can think of this as a big inner product, right? So it's something we did very early on. And so it will be v1 times, this will be the first column, first row, second column, second row, so on, so on, so on. The lambda 1, lambda 2, they're just constants, so they come out the front. So they're here, here, here. And then we have column, row, over and over, right? So they look like, I guess I'll erase it. It looks like these they're outer products. Amazing. Which we know are actually projection operators, right? So little outer products, if they're made out of unit vectors, they're actually projection operators. This is the big deal here. So what is going on? And so we could write it as this sum, right? So we've got this nice expression here. It's a sum of these little outer products with a weight, and the weights are the eigenvalues. This is called the spectral theorem for symmetric matrices. It's not because it's spooky, because we talk about eigenvalue spectra and spectrums. What this means is, so we've got these little outer products, right? Not inner products, outer products. So when we multiply an x, this vector comes along, it's an inner product with it, and then it gets multiplied by itself again. So we're projecting, and we know how that works, that means it's projecting x into that direction, right? So it's taking the portion of x that is in the v1 direction, say. So we're chopping it out. And then it just simply multiplies it by the eigenvalue. So it's doing exactly this thing that we understand diagonalization to do. It's just that when we have symmetric matrices, the mechanics of it are very simple. Very simple. The change of basis is not a horrible thing. Really a beautiful thing. Okay. But this is only for symmetric matrices. So does that sort of make sense? So we have right? We have these pieces here. They're all little choppers, right? They chop X up. I guess I don't, yeah. So each projection operators, right? Each one, let's write that. Each one chops, right? So it chops out a piece of X, right? For A times X. Each one chops out a piece of X, and then, right? And then scales by lambda. Right, stretches it or shrinks it, whatever it is. And then you put them all back together, right? These plus signs in here, you're going to simply add them, sorry about that. You're going to add them all back together. So chop it all into pieces, do all the stretches, and then add them back together. So kind of algorithmically, if you like, that should make sense. It seems a very practical thing to do. And it just naturally comes out for these very special matrices, symmetric matrices. The big deal later on, not far away, is that A transpose A, as we've talked about, and AA transpose are symmetric matrices. It doesn't matter if A is rectangular, they're always symmetric. If it's full of apples or bananas and campfires, doesn't matter, right? Okay, that is great. And so here is our example. So it turned out we were playing around with a symmetric matrix. Sneaky. Symmetric all along, right? So in fact, we can construct our S and our inverse of S very simply. Now it's going to be Q and Q transpose, right? So Q again is always just the S matrix. It's going to be V1, V2, the unit vectors. The inverse of that matrix is just the transpose. Take transpose. Very simple. Which is the inverse we had before, but we didn't really say anything about it. Easy. Very nice. So now we can write A. We've looked at how A functions, right? So instead of, this is S lambda S to the minus 1, more generally. Just putting all these pieces together, right? So here's our Q, Q transpose, and lambda. And then we've got this new thing, which is this these outer products, right? So here's this is lambda 1, V1, V1 transpose. Maybe I can write that, right? So lambda 1, V1 with a hat, V1 transpose, and then this is lambda 2, V2, V2 transpose. Two projection operators, right? The first one projects, if A times X, it will project X onto the 1, 1 direction and then multiply by 3/2. The second piece projects it onto the, I guess that's right, 1 minus 1 direction. And then I think that's not what I want. Q is, it should be minus 1, 1. Thank you. Thank you, brain. Betrayer. Okay. Get too happy with yourself. You're the one who made the mistake in the first place. Projects it. Yeah, right. Sorry. Projects it onto the minus 1, 1 direction and multiplies it by 1/2. And then we add them back together, right? So we divide X into these easy, right? So this chops X, well, let me say it like this, breaks X into, right, for A times X, this clearly breaks X into two orthogonal pieces for which, A times V1 and A times V2 are very simple because they're the eigen directions. Right, and then combines, and then recombines. Well, imagine music coming in and you break it into two pieces, right? You break out the violin and the tuba, right? You break it into these two pieces, put the volume of one up, put the volume of the other one, you know, whatever you want to do, and then put them back together. That's the idea. So it's for things that add up in simple ways. Okay, fantastic. We've gone from S lambda, S transpose, S inverse of S, to now Q lambda, Q transpose. Beautiful story, works for real symmetric matrices. And there are generalizations, but that's what we're working on now. And you can write it as these matrices, or you can write it more, even more economically as some outer products. And the outer products, you know, they're lightweight objects, right? They're very lightweight objects. We don't have to make a big stack of matrices. And they even more clearly show you what they're doing. They're projecting, scaling by the lambda 1, lambda 2, lambda 3, and then recombining things. So that is how A works for symmetric matrices. It is underneath it really a diagonal matrix that has preferred directions that are orthogonal to each other, which is pretty incredible.